The last section we're going to look at for chapter 5 is on integrating functions that involve inverse trig functions. And so those rules we learned in the last section for taking derivatives, we're going to apply them now to work on integration. So there's three main formulas you're going to need to be familiar with here. So the integral of dx over the square root of a squared minus x squared. So if you see something in this format, that means you're working with arc sine of x over a plus c. The integral of dx over a squared plus x squared is equal to 1 over a times arctangent of x over a plus c. So if you think back to the derivative arc sine was 1 over the square root of 1 minus x squared, if you just had an x in here, this basically is accounting for that chain rule if you have anything other than just an x here. Same thing here with the arctangent. This is as if you had a chain rule. If you took the derivative with the x over a and simplified it, it would give you this. Patterns is what you're looking for. So when you see something in this format, you're going to know that it fits the arctangent rule. When you see something in this format, you know it's going to fit the arc sine rule. And then there's one more. If you see something in this format, integral of dx over x times the square root of x squared minus a squared, that fits the arcsecant rule. A couple things to remember. Arcsecant and arctan both take the 1 over a. Arcsine does not. Arcsecant technically should have this absolute value of x over a because you can't, that argument there can't be negative. So let's look at an example. Suppose I want to do the integral of dx over the square root of 4 minus x squared. So if you look at those three rules that you just wrote down, hopefully one of those rules is jumping out at you. Do you see that this fits the first one, the arc sine rule? So a, this is a squared, so a would be 2. So this would be the arc sine of x over 2 plus c. Straightforward, no u sub involved. Let's try this one. We've got the integral of dx over 2 plus 9x squared. Hopefully if you look back at that list, you'll see that this fits, it looks a lot like the arctan rule because it doesn't have the radical and it's the sum of those two terms in the denominator. The thing that's a little different about this one is that it doesn't have just an x here, it's 9x squared. This last example just had an x, so we could go straight to the rule and just say x over a, where a was 2. This one's a little bit more involved. So what we're going to do is we're going to do a u substitution, and we're going to let u equal 3x. And notice that a is the square root of 2 because this would be a squared. So derivative of u, of course, would be 3, so that means du over 3 replaces the dx. So go back here and make your substitutions, and you've got 1/3, that's from the du over 3, times the integral of du over, now I'm writing this to be emphatic here, the square root of 2 squared. You can just leave it 2 as long as you know that that's your a squared value, plus u squared, because remember u was 3x and you have 9x squared here. So this is the format we need it to be in for the arctangent rule. So this means we're going to have 1 over a times the arctangent of u over a plus c with the 1/3 in the front, and then we have to remember to make the replacement for u, which was 3x. Check this by taking the derivative. You don't have to write this down, but just take a look. If we do a chain rule for the arctan of 3x over the square root of 2, we get 1 over 1 plus that expression squared times the derivative of the inner function, which would be 3 over the square root of 2. Those 3's would cancel. This radical 2 and this radical 2 became a 1/2 in the front. Square this expression in the parentheses. That gives me 9x squared over 2. Get a common denominator on the bottom. Use the reciprocal, so that 2, don't have to use the reciprocal yet, just cancel that 2 out with the 2 that you have in front. And this was what we started with. This was our original integrand in the last question. Which rule does this look like it fits? Hopefully you recognize because you have the x in the front and the square root of the x squared term minus the a squared term. This is the arcsecant rule. So we're going to let u equal 2x again. Anytime you have anything other than just a regular old x here, you want to do a u substitution. And notice that a is 3. du over 2 replaces the dx. Now, notice also that when I do this u substitution, I've taken care of the 4x squared, I've taken care of the dx, but I still have this x down here. I have to do something with that. Remember, we don't mix x's and u's. So this u equals 2x expression, I'm going to isolate the x in that expression by dividing by 2. So let's go back and rewrite our integrand with all of our substitutions. The 1/2 goes to the front. That's your du over 2. The denominator becomes u over 2 times the square root of u squared minus 9. You can write the 3 squared if you want to, or just leave it as 9, as long as you know that's a squared. Now, remember, this over 2 is a constant multiple. So what happens with this over 2 and the 2 that's in front? Those are going to go away. And now I have exactly what I need. Look back at your arcsecant formula. This is it. This is the format I need it to be in. So a lot of these problems is about taking the integrand, and if it looks like one of those 3 formats, you might have to do a u substitution and do a little algebra to get it into the exact format that you can work with. So we have 1/3, because remember a was 3, arcsecant of the absolute value of u over 3, and then just remember to replace u with the 2x that you substituted in the beginning. I'm going to skip the details, but if we take the derivative and use a chain rule and do some algebra to get it simplified, it does actually give us what we started with. So we know we did it correct. All right, compare these integration problems. We're not actually going to work each one of these out just yet, but I want you to look at them and kind of compare the difference. The first one to me looks like it fits the arcsecant rule. The second one, I think we could do a u substitution, because notice that this one has an x in the numerator. So if we let u equal x squared minus 1, the derivative would contain the x that we need it to. The third one I'm going to address in a moment. Let's go back to the first one. It fits the arcsecant rule directly. A is 1. X squared minus 1 gives me 1 over a. Of course, a is 1. Arcsecant of the absolute value of x over 1 plus c. That's directly from the rule. The second one would be a u substitution. If we let u equal x squared minus 1, du over 2 would equal x dx. So the integrand would turn into this. Notice where this u to the negative 1/2 comes from. We would have had du over the square root of u. So that's u to the 1/2. Bring it to the top and use your power rule. You'll get this for your antiderivative. The last one, we actually haven't learned how to do yet. So this is one we can't do at this point. But I wanted to show you these 3 because I wanted you to make that comparison. And this is the point with these integrals where you want to start thinking about strategies. And will a u substitution work? Does it fit one of those 3 inverse trig functions? If I do a u substitution, can I make it look like one of those 3 inverse trig rules? Those are the kind of strategies you want to start thinking about. How about these problems? Same things. Go through each one and kind of think about how you could approach it. Would a u substitution work? Look at the first one. If we let u equal the natural log of x, the derivative would be du over x, or du rather would equal dx over x, right? 1 over x dx, which is exactly what we need because we have a dx over x in the denominator. So this would be the integral of 1 over u du, because the u replaced this natural log of x and it was in the denominator. So that would be natural log of u, which is natural log of x. How about the next one? Can we do a u substitution on this? If we let u equal ln of x again, we have the same du expression, which is good because we've got du over x, or dx over x again. The difference here is that the natural log that I replaced with u was in the numerator instead of in the denominator like it was over here. But we can integrate this using a power rule, right? This would be u squared over 2. So that becomes natural log of x squared over 2. The last one, again, we haven't actually learned yet. So this will, to integrate natural log of x is a technique we'll learn when we get to chapter 8. So we'll do that later. Let's try this one. So this looks like it might fit the arcsecant rule because it's got something x squared minus a squared, but it doesn't have that x we need in the front. So let's try a u substitution on this. This one's not very intuitive, so let's go through it. If we let u equal e to the x, What is du dx equal to? Of course, that would be e to the x dx. So what do I need to solve for in the expression? I need to solve for dx. So in this expression, if I divide by dx, I can replace dx with du over e to the x. But remember, what was e to the x right here, because we don't mix x's and u's, what was e to the x equivalent to just a second ago? That was equivalent to u. So this becomes du over u, replaces the dx. Take a look. So just a reminder, e to the 2x, of course, is e to the x quantity squared. So that replaces du over u times the square root of u squared minus 1. And that's the arcsecant rule that we need. So a is 1. So we have 1 over 1 times arcsecant of absolute value of u over 1. And then just replace u with the e to the x that we started with. Okay, let's give this one a try. We've got integral of x plus 2 all over the square root of 4 minus x squared. This looks kind of like maybe arcsine. I've got a squared minus x squared under a radical, which looks good. The problem is I have this x plus 2 in the numerator. If I try to do a u sub with the 4 minus x squared, I will get a derivative of negative 2x, but I have x plus 2 in the numerator. So that doesn't exactly work. So what I'm going to do is I'm going to separate numerators. Remember, you can always separate numerators. So I'm going to write this as two separate integrands. So I've got the integral of x over the square root of 4 minus x squared plus the integral of 2 over the square root of 4 minus x squared. One of these fits an inverse trig rule and one is a u sub. Can you tell which is which? The first one is the u sub, because if we let u equal 4 minus x squared, we get du over negative 2 equals the x dx. So we have negative 1/2 times the integral of 1 over the square root of u du, which becomes negative u to the 1/2. Pause the video and do the power rule. This is u to the negative 1/2. Add 1. You should get this expression when you simplify it. And then go back and replace u, of course, with the 4 minus x squared. The other expression is the arcsine rule. Take the 2 to the front. That's a constant multiple. And you can see right away that a is 2. There's no need for a u sub here because I just have x squared. I don't have something else squared, just a plain old x squared. So we have 2 from the constant multiple in the front times the arcsine of x over a, which is 2 again. So now put these back together, and there's our final antiderivative. Okay, let's try this one. We've got the integral of dx over x squared minus 4x plus 7. This doesn't look like any of the rules that we've worked with so far. We've got 3 terms in the denominator. A u substitution won't work because even if I let u equal the denominator, I don't have anything to match it with in the numerator. So we're going to talk about a new technique that's called completing the square. And I don't remember if we did this semester in AP Calculus. I think it may have come up once or twice, but we've actually done completing the square. You would have done this probably in pre-calculus or college algebra. And so what that means is we want to rewrite this expression in this denominator, this trinomial, as the sum of 2 squares. Notice, here's the steps. What you're going to do is you're going to take the middle term and you're going to divide it, just the coefficient, you're going to divide it by 2 every single time. And we'll go over this again in the office, but just follow along with me as best you can. We're going to take the b value, we're going to divide it by 2 every single time, divide it by 2. We get negative 2, and then you're going to square it, which is 4. So then what I'm going to do is I'm going to write x squared minus 4x plus 4. So that's the 4 I just got from that little technique. That's the first 2 terms. But then on the outside of those parentheses, I'm going to put a negative 4 and a plus 7. Why am I doing this? Well, the 7 is from the original expression, but this negative 4 has to be there to balance out the 4 that I've added in order to complete the square. So in other words, I've added 4 from this previous step, and at the same time I've subtracted 4. So I've really just added 0, which is allowed. You can add 0. As long as I add 4 and subtract 4, I'm okay. So what does this do for me? Well, this x squared minus 4x plus 4 is now a perfect square trinomial that breaks down into x minus 2 quantity squared. Negative 4 plus 7 breaks down to a 3. And so I'm going to put this back into my integrand now. So this original denominator is this exact same thing, just rewritten. So this fits the arctan rule if we let u equal x minus 2. The derivative, of course, would just be 1, right? So du would equal dx. A is square root of 3. So when we put that back together, we have 1 over the square root of 3, 1 over a, times arctan of u over a plus c, but u is the x minus 2.